Today we will talk about real analysis lecture 4. Yep, the beginning of lecture 4. And I'm going to cover proofs and fields. So you can find out the proof for this statement over here. And the statement is rational numbers do not satisfy LUBP, which differentiate the rational numbers from the real numbers. Least upper bound property, if you don't remember that. Look at the previous lectures to understand. So theorem, which we're going to prove, we're going to spend the bulk of this part proving this. Set E equals to, so let's define E, not like, and this is just a regular E, no line in the middle. There's a line in the middle. Consider that the even number set, even though it's not an actual definition. So this is just a part of the theorem. So this is the set. This is actually a part of proving Q doesn't have LUBP. Wait, is this written correctly? Yeah, this looks very weird. So let's just call it E, Q, and Q rationals. Q is greater than 0. And Q squared is less than 2. So prove E is bounded above and has no supremum in the rational numbers. So this is the set that proves the least upper bound property is not existence. This is just actually a part of the previous proof. Let Q be an E because let Q be an element in E, then obviously Q squared, which is less than 2, which is less than 4, which means 4 minus Q squared is greater than 0. Makes sense? Which implies 2 minus Q times 2 plus Q is greater than 0. So all of these statements are greater than 0. Makes sense, because if it's Q squared is less than 2, then Q squared is obviously less than 4. Which also implies 2 minus Q is greater than 0, which implies Q is less than 2. Thus, for all Q and E, Q is less than 2. So this part makes you feel like you already derived that, because if Q squared is less than 2, obviously Q must be 2. But remember, we're talking about the rationals here. Remember? Then 2 is an upper bound. Is an upper bound. We now show supernum E do not exist. It doesn't exist. By contradiction, so assume we call it exists in Q, call it X. Now the previous statement, X is greater than 1 and X squared equals to 2. Thus, they exist in M and natural numbers such that this is basically the definition of a positive fraction, which is such that M is greater than N. So, n times x is an n, the natural numbers. This is a very tiring proof. I've been trying to avoid making this video all week, but you just got to get the work done, am I right? Oh god. So let's make it set as such that for all k in the natural numbers, k times x is n. Note n is in S, which implies S is non-empty. So, by the well-ordered property of the natural numbers, S has the least element KO in S, since it's a part of the natural numbers. Define K1. Okay, this is already K0 KOX minus KO, which is in the integers. Since x is greater than 1, K1 equals to K0 minus 1 greater than 1. So K1 is in natural numbers. This is already getting pretty weird. Since x squared equals to 2, 4 minus x squared is greater than 0. So we're kind of getting to the same region over here. What if we look at the same stuff all over again? Yeah, I feel like it's the same stuff. So okay, my notes is very weird. So this factoring x squared equals to 2, so 4 minus x squared is greater than 0, and we factor it out. 2 minus x is greater than 0, x minus 2 is less than 0, you could say that. I don't want to say that out. So that's true. K1 equals to K0 x plus 1 0 2 minus 1 equals to K0. So this is already getting contradictory. Thus K1 is in the natural numbers and K1 is less than K0. So by this contradiction with all these random k variables, it's not true. And he actually added extra stuff, but I am not gonna write that down. Oh god. In fact, you know what? I'll write that down for anyone who's interested, but I'm not gonna explain any bit of it. As an 11-year-old boy, this proof really, really annoys me. Once I'm writing on this whiteboard, I'm not even sure if I'm writing the correct stuff, but it probably doesn't make sense. Look carefully, you math majors. If this makes any sense. Oh shoot, xk0. So I'm not gonna explain any bit of it because this looks annoying. I just wrote it down and didn't care because right now, why would I want to care? So it's this stuff. So think of all of this stuff, get this information absorbed. So this sentence actually makes quite sense to me. So this and thus k1 is less than k0, which really doesn't make sense. So k0 is not the least element in x, it's k1. But hey, we define k0 as that. It's a contradiction. So all these weird stuff, and then we get to these, and that contradiction. Those are the only parts that make sense. So after finally killing this proof, where are we gonna end this part? Okay, so I'll see when we're ending this part. And part 2 might take some time because I don't know if you're going to find time to continue writing notes. But here's the definition. Very interesting definition. You should look at this. A set F is a field if it has two operations, plus and times, like, this and this. Oh my god, this reminds you of a graph and parallelogram rise, and this reminds you of vertical lines. Geometry, people, this is not anything special. It's plus and times. Oh god, this looks insane. I hate this, bro. It confuses me to the brink. Just use x squared, okay? Or for all the cool people out there, just use a dot. Oh my god, whoever uses x as a multiplication sign now these days. Like, the dot is much better. For example, 4 times 2. Much better to write. Anyway, so plus and times. A1. These are actually very basic definitions. If x... These are very basic, but they make them look so technical. That's the fun part. I can flex on everyone, even though these are the pretty simple definitions. So, these are axioms for sets. No, for fields. These are fields. So, say there are two elements, x and y, in the set, in the field. X plus y is in the field. So there must be kind of a definition, and we'll see what kind of definition we do. So this is so these are properties. So A2 is a commutative property, which, as defined in very weird mathematical lingo, this just looks so weird to the average person. Like, this is commutatively. I thought it was like x plus y equals y plus x. Yeah, you'll see that over here. The first sentence is literally just say if they're part of the set, then if they're part of the field, then this must work. This is a literal property you learn. It's not that hard. Just if you see this phrase over here, just know if x and y is in this field. If x and y are in the field, then that's how it works. Associatively, guess how you're going to write this one? Well, this time you're actually going to use 3 variables because that's how you did it in elementary school as well. Okay, that's someone calling. Let's see. Okay, so my sister needs to take medicine. My sister comes here. In fact, give me a second, I'll tell her. Didi, you have to take medicine. Didi, you have to take medicine. Okay. If you were able to hear that, I don't know if you were able to hear that. She's a very annoying. I'm just joking. Well, we do get arguments sometimes. Anyway, so guess how you're gonna write the next part of it. It's not that deep. Literally, just it's. If you guys weren't able to guess this, then you need to review basic math. Or is it just because I'm so accustomed to basic math that you all advanced people can't understand a slither of this? Maybe, but you should know the associative property by now. It's kind of a problem if you don't. Kind of a problem. So these are the properties: commutatively, associative property, and A4, the identity property. There exists an element which we're going to denote by 0. Don't say this is 0. It's going to be denoted by 0. It's not 0 though. It's just going to be denoted by 0. Such that for all x and f, element 0 plus x equals to 0. In fact, let's call it O. Okay, there exists an O in f such that for all x and f, O plus x equals to O. What? No. O plus x equals to x. I made a mistake in my notes. Yay! So, it's x. Sorry, x. This is multiplication, something different. So you said O and F. Why O? Because we don't want to make it look so much like 0. It could be anything. It could be 5. Maybe 5 is your special 0 and you could create your own field for fun. Do you guys even feel like that's fun anymore? Do you have any fun in life anymore? Or you're just like, oh my god, life is all about studying. Well, for all x and f, there exists a negative x and f. What? There exists a negative x and f such that x plus negative x equals 0. I don't think this is true for the natural numbers. Yeah, it should be true for the naturals because they don't have negatives. So A5 is kind of bad. But like x plus negative x equals to 0. Equals to 0, yeah. M1. Multiplication properties now. This is again like the definition. Very basic. See, I'll use a dot. So now we have the commutative property of multiplication. I know you could just do x, y, y. I was actually planning to do that, but second one I just put too much space. But like, so for all x and y and f, x times y equals to y times x. Commutatively, okay, that was wrong. Wrong pronunciations. Again, these definitions take time. So that you know the associative property exists. In fact, just know at this point you should know how this is gonna look like. If you don't, I'm pretty sure you have a problem. So sorry, this doesn't look right. X times y times xyz equals to xy z, and you know that because associative. Again, if you don't know associative, something's wrong with you. These multiplication ones are super similar to the addition ones. For an element, let's call an element I without the dot. In F, there exists an element I without the dot, or U. Let's call it U. Such that for all x in F, U x equals to x. Reason I'm calling it U because I have nothing else to call it, and if you call it 1, it'll throw people off. It's just defined as that. It's actually, yeah, so let's call it U, okay? For all x in F, not 0, there exists an x to minus 1 power. You should know exponents. In fact, you should know most of this basic stuff, such that x times x to the negative 1 equals to 1. Is that supposed to be U or 1? I'm not sure. And now finally, special D. What does this D mean? It means distributive property. So for all x, y, z, because you need 3 for the, or 3 or more. You could put always more, but like 3 is the least amount you need. So x plus y times z equals to xz plus yz. And same thing is for negative numbers, but technically you could just say x negative y plus negative y, so there's no need for that. So now here are some examples, and then we're going to be done. We won't talk about ordered fields just yet. Actually, the integers are not even. What? Well, that's weird. Okay, I'm just gonna ignore that because I'm not entirely sure. So EGZ, I'm not gonna say EG the not integers because for some reason it's under non-EG, even though you'll see why I'm in such weird. But like the rational numbers, I can tell you if that's an example. X. Oh yeah, this. Have you ever seen this? Actually, this wasn't actually in the lecture. I just knew about this. I'll relieve it one letter by a time. Vector fields. vector fields and I show the operations with the two vectors. If you don't know what a vector is, it's basically something. It's like a line. I'm a kid. What do you expect? And it has components. It's like slope only. It's changing. So keep changing x. That's basically the component form. Anyway, yeah. So those are just a side note between vectors. And also, if you want to know, add vectors, you just, I'll say for subtracting, negative numbers, it's kind of the same. So you should just not, it's not that hard. Even it's the same thing with matrices. And multiplication is a bit different. I think it's like a dot product. I don't remember how to do that. And here's some examples. See, this is the reason why I was confused when I put non-EG under the integers. Because this is an example. So that should obviously be an example as well. 0, 1. How does this work? Well, let's define 1 plus 1 equals to 0. It works. And Z3, integers 3, 0, 1, 2, 2, A plus B equals to C, mod 3. So modulars is basically give you the remainder. Let's talk a bit about number theory and modulars. So what is 6 mod 3? Well, that's 0 because modulars give you the remainder. 6 mod 4 is 2. 6 mod 4 is 1. Mod 5 is 1. So 6 mod 6 is also 0. 6 is 0. 6 mod 7 and onwards, it's always going to be 6. Always. Otherwise, this is 0, this is 1, this is 2, this is 0. You think it'd be 3. It's not. It's 0 only. And 2 is also 0. 1 is obviously 0. So basically it's 0, 0, 0, 2, 1, 0, 6. So that's modulars. And mod m equals to remainder and divided by m. So now we understand that we just, like for example, 1 plus 2 in the Z3 universe, this is actually, yeah, this would equal to, not 3, but 0. Now, what's 2 times 2? Well, that's going to be 1. What's 3 plus 1? That's going to be 1, because modulars. This still works. This works with our axioms. But later we'll see order fields really help things a lot. And oh wait, so as you see, z and any finite number, and I'm pretty sure z should also be, because obviously z infinity will work. Those are all fields. Now here's a quick theorem, which its proof is nothing. Well, I didn't put it, but I just put it's an axiom, but is there going to be a proof? I don't remember if there was actually a proof for this, but I don't think there actually was a proof. Maybe there was, but I just said it was an axiom for all x and f. 0 times x equals to 0. And I said proof is an axiom. And then after this we go over order fields, which are basically stricter fields. And I'll just tell you something cool. Z2, Z3, Z n, which all of which supply under mod n. None of these are examples. None of these work for ordered fields. So you'll finally see some order. You can probably guess what it means, like x plus y, like transitivity properties and all that stuff. You could probably guess that already. Like, yeah, you could probably guess that. So we are done for today's part of the lecture. So goodbye, everyone.